The next word problem says find the force F that balances the system of forces shown below. So 14 backwards, some unknown force F, 3 backwards, and 10 forwards, 9 forwards, and 60 newtons forwards. So we're going to try to solve this, and when you're ready, unpause. So let's just draw this picture here. This is the point where the forces are being applied. So you have a force of 10 newtons forward, so I'm going to call that one plus 10. You have a force of 9 newtons forward, so that's going to be plus 9.4. And you have a force of 16 newtons forward, so that's going to be a plus 16. And you also have a force of 3, but it's backwards, so that's going to be negative 3. And you also have a force of 14 backwards, so that's going to be a negative 14. And you're trying to find out what is the unknown force F that is going to keep the system balanced. What that means is that the acceleration has to equal 0. Nothing has to, it has to be either stationary or moving at a constant speed, or just say that the acceleration is 0. Or another way to look at this in terms of Newton's second law is that the total force has to equal 0. So the sum of all the forces are going to equal 0. Or total force equals 0. So you just have to add up all the forces and set them equal to 0. So the forces that are present, you have the unknown force F, and the minus 14 backwards, the minus 3 backwards, the plus 10 forwards, the plus 9.4 forwards, and the plus 16 forwards. Those are all the forces. So add them all up and set them equal to 0. And then you can do the algebra to solve for F. F will come out to be negative 18.4 newtons. So the negative makes sense because that means that F is pointing backwards. All right, now try this one. It says a force of 50 newtons is used to pull a cart over a distance of 55 meters. If the force is directed at 33 degrees relative to the horizontal, what is the work done by the force? So go ahead and pause, try to solve this, and when you're ready, unpause. Let's write down the givens. So first one is 55 m. Distance, I'm going to call that x. Meters is distance. And 33 degrees. Degrees is an angle. And let's see. 15 up top here, 15n. So n, that's Newton, so this is a force. And we're trying to get the work. So the picture looks like this. You have some kind of an object, and you drag it over some distance. So this is actually going to be delta x, the distance traveled. And you apply a force of at an angle. So from the center here, the force is applied at an angle of 33 degrees, and the force is applied in this direction, and trying to get the work done. So in this case, the work is going to be the force applied, the distance traveled, multiplied by the cosine of the angle between the distance and the force, or the displacement and the force. So here, plugging in, the work is going to equal 15 multiplied by 55, and 50 newtons multiplied by 55 meters, and times the cosine of the angle, which is 33 degrees. And that will give you a work of 691 joules. So next word problem says a 0.5 kilogram ball is thrown into the air. It is initially 15 meters above the ground. When the ball is moving at 6.2 meters per second, find its initial kinetic energy, its initial potential energy, its initial total energy, and also its final total energy. So go ahead and pause, try to solve this, and when you're ready, unpause. Let's write down what's given. So 0.5 kg or kilograms is mass. 15 meters is distance, so I'm going to call it x for now. 6.2 meters per second, that's velocity. And that's about it. And we want to find, let's see here, so for A, the initial kinetic energy. So KE initial, and B, the initial potential energy. So PE initial, and C, the total energy, or the total initial energy, and D, the total final energy. Okay, so first we can get the initial kinetic energy. The initial kinetic energy is going to be 1/2 the mass times the velocity. Well, actually, we're not ready to do that just yet. Let's try to interpret what's happening here. So this is the ground. The ball is thrown up, and when you first locate it, it's somewhere up here at 15 meters. So instead of x, this is actually y here. So this is y initial. That's the initial height when you first see it. And it's moving at a velocity v, so I'll just say velocity v in this direction, so that's going to be the initial velocity. And you're trying to get the initial kinetic energy, the initial potential energy, and the initial total energy at this point, and at any later point, you're trying to find out what the final energy is going to be. Okay, so now we can plug in. So first we can get the total kinetic energy, so excuse me, the initial kinetic energy, so KE initial is going to be 1/2 the mass multiplied by the initial velocity squared, which is going to be 1/2 the mass, which is 0.5, multiplied by 6.2 squared, and that will give you 9.61 joules. We also can get the initial potential energy, so PE initial is going to be mass gravity multiplied by initial height, so that's going to be 0.5 times 9.81 times 15, and that will come out to be 73.56 joules. And now the total initial energy is just going to be the kinetic plus the initial kinetic plus the potential, so 9.61 plus 73.56, and that will give you total initial energy of 83.2 joules. And we're going to assume that nothing interferes with the ball as it's moving through the air, so that energy is conserved, so which means that the final energy is going to equal the initial energy. So we're using conservation of energy. So then the final energy in this case, if nothing interferes with the ball, is going to be 83. It's going to be 83.2 joules.